So, hello to everyone who's watching on YouTube. I guess I'll start in 5 to 10 minutes so that a few people can join the meeting in person also. So, I'm waiting for like 5 to 10 minutes for other people. So, yeah, I'll mute myself till then. Okay, I guess since no one has joined the session yet, we can just get started as it is. So, just to reintroduce myself once again, hello to everyone. I'm Lakshya Sakhi, the Discrete Maths problem solving TA for the Monday 6 to 8 p.m. sessions. Today, we are having the session from like 7 p.m. onwards because of some like unavoidable delays in traveling, but apologies for that. So, this will be our eighth session, I believe, and in this session we'll be covering again, like we'll be continuing from where we left off last week, problems related to graphs. And in this week's content, we'll be covering problems related to graph coloring and yeah, mostly graph coloring type problems or Hamiltonian paths problems. Yeah, I guess then we can get started. I'll just share my screen and we'll start discussing the questions. Okay, so I hope my screen is visible to everyone. So this is again a great session. And first of all, like since we'll be using before discussing the problem straight away, we have like something like 11 problems for today. Before discussing these problems, let's just cover some notations first because these notations will be using a lot in the questions. Although these kinds of these notations have been obviously uh, told in the lectures also, but I guess we can just discuss them nonetheless again so that everyone is on the same page. But I'll be assuming that while going through the questions, I'll be assuming that you guys have seen the lecture videos. So there's that. But still, I'll just be discussing this kind of question. So what does a KN what do we mean by a KMN? A KMN is nothing but a complete bipartite graph with m vertices on one side and n on the other. So as we know in a bipartite graph, a graph can be partitioned into two sets of vertices. So let's say the first set of vertices is m contains m vertices and second set is n vertices. And a complete bipartite graph means just that every each of these m vertices will have an edge to each of these n vertices. So there will be a total of m times n edges in the graph. And none of these m vertices will have an edge between themselves, and similarly, none of these n vertices will have an edge between themselves. Uh, so yeah, I hope everyone is familiar with bipartite graphs. And then what's a KN? A KN is a complete graph on n vertices. So it just denotes a graph containing n vertices and like each pair of vertices has an edge between them. And this is what we call KN. And similarly, what is PN? A PN is just a graph which is a path of just n vertices. So if there are just n vertices and it just consists of a path like connecting all of these n vertices, so there are just n minus 1 edges of that path in the graph. That is what we call a PN. Similarly, another notation which I would like to denote is let me CN. So CN is CN is just a cycle graph, like a graph which is just a cycle on n vertices. Just a cycle on n vertices. So if there are like four vertices, then you can just form a cycle connecting those four vertices. It would be something like a quadrilateral or something, and that is what we call a CN. So that will be C4, a cycle on four vertices. Similarly, a CN in general denotes a cycle on n vertices. So I guess since we are clear with the notation, we can move on to the questions then. So first question is, let Km comma n represent a complete bipartite graph where m and n are positive integers. So again, complete bipartite graph, we already know like what does Km n denote, and what is the chromatic number of this graph. So in this week's lecture, we have already discussed like in these week's lectures, it has already been discussed what is a chromatic number. So just revising. So what's the chromatic number of a graph? So So chromatic number is nothing but the minimum number of colors required for a valid vertex coloring to exist. So chromatic number is minimum number of colors required for a valid vertex coloring to exist. And what do we mean by vertex coloring? We just mean that like a vertex coloring is a valid vertex coloring if every vertex can be assigned a color such that no edge in the graph, the two endpoints of each edge of the graph have different colors. So each edge of the graph has two vertices as the endpoints. So if both the endpoints are different colors for all the edges, then that is what we call a valid vertex coloring. And chromatic number is just the minimum number of colors required for a valid coloring to exist. Okay. So our answer actually here would be like Kmn is a complete bipartite graph where Mn and are positive integers. What's the chromatic number? For this, what we'll claim is our claim will be that chromatic number for this graph, chromatic number is nothing but equal to 2. And this will be our claim. And why will this be true? Like it can be seen intuitively also that a bipartite graph is like there are vertices on the left side, there are vertices on the right side of the graph. So there are two sets of vertices. And we just color one set as the first color and the second set as the second color. And since all edges of the graph are between these two sets, so all edges will have different colors as different colored vertices as endpoints. So this is the high level idea, but note that once again, we need to also show that this is the minimum number of colors required. So while showing anything which is minimum, we want to show an upper bound as well as a lower bound. Like we want to show that the minimum number of colors required for this graph is 2. We want to show that this graph can actually be colored using 2 colors. And we also need to show that this graph cannot be colored using 1 color. Note that the distinct, like this is because chromatic number is the minimum number of colors required. So you can't use less than 2 colors and you can exactly do it using 2 colors. So these are the two claims we'll need to provide. So maybe we can just write it down. So we need to show that we can color the graph using 2 colors. Also, we need to show that we cannot color the vertices using just 1 color. And I'm claiming this part, the lower bound part, like we need to show that we cannot color the vertices using just 1 color. This part I'm claiming that this is trivial. And I don't want to write an explanation for this, but I'll just discuss this orally. And why is this trivial? Because we know that the endpoints of an edge, there are two vertices which are endpoints of an edge, right? So we know that both the endpoints should have different colors. So we always require at least 2 colors for a valid coloring to exist. If there exists at least one edge in the graph, then both the endpoints of that edge should have different colors, right? But if we are just using 1 color, then both the endpoints will be having just 1 color, the same color. And that's why it won't be a valid coloring. So that's why we cannot color the vertices using just 1 color. And this part is somewhat obvious and I don't want to write the explanation for this. So now the only thing remaining for us to show is that we can color the graph using 2 colors. This is what we need to show. And how do we show this? So to show that Amn can be colored using the 2 colors. Let's just assume the colors to be, let's say, C1 and C2. Let's just assume there are 2 colors given to us, and we'll show that given 2 colors, we can color the vertices. And the intuitive high level idea is, so that's what I'll just be writing down, that we can color one set as 1 color and the second set as the second color of the bipartite graph. Okay. Assume the colors to be C1 and C2. So there are two colors given to us, which are C1 and C2. And now, since the graph is bipartite, so since Km and Km comma n, which is given to us, the answer for this Km comma n is bipartite, the left side. So in bipartite graph, I'll just denote the one side, which is the vertices of the m vertices as the left side. I'll refer to it as left side. And the n vertices, I'll just refer to it as the right side. Like it doesn't matter, anything can be left or right. But just for convention, I'll just be saying that. The left side vertices can be colored with C1. Okay, with C1 and right side vertices can be colored with C, which is okay. And now we need to show that this is actually a valid coloring, right? If we color the left side as C1 and right side as C2, then this will actually be a valid coloring. And why is this the case? This is because, like, why is this a valid coloring? Since every edge in KMN is between the left side and right side vertices. So one endpoint of the edge is always on the left side and one is on the right side. So every edge has endpoints as, hence every edge has endpoints colored as C1 and C2. So one endpoint will always be C1 because one endpoint will be on the left side. Other endpoint will be C2 because other endpoint will be on the right side. Right? So this is a valid coloring. Hence, this is a valid coloring. So this is a valid coloring using two colors, and we can't do it using distinct colors. And like note that why this part works in bipartite, but using two colors may not necessarily work always, is because the left side in bipartite graphs, we have the special property that the left side vertices don't have an edge between themselves. Like there does not exist an edge from one vertex on the left side to the another vertex on the left side. Every edge is between the left side and the right side vertices. If there was an edge between one left side and two left side vertices, then both endpoints can't be colored with C1, right? So that's why this argument might fail. This argument fails in like non-bipartite graphs. Yeah. And now maybe we can move on to the second question. So in the second question, we have that second question asks, what is the minimum number of colors required to color a complete bipartite graph containing n vertices? So now we are given a complete bipartite, not a complete bipartite graph, but a complete graph. And what is a complete graph? Like we have n vertices and an edge exists between every pair of vertices. And now we need to find out the minimum number of colors required to color it. And in this setting, we'll claim that the answer actually is n colors. That a complete bipartite graph, for coloring a complete graph, not a bipartite graph, sorry. For coloring a complete graph, we will require n colors. And again, for this to hold, we need to show that the graph. So I'll denote this complete graph containing n vertices as just k. Like because like as I already discussed the notations, okay, that we call this as kn, a complete graph on n vertices. So we need to show that kn can be colored using n colors. And note that this part is trivial. This part is trivial. Like, why can Kn always be colored using n colors? So what we can actually claim is that any graph on n vertices can always be colored using n colors. And why is this the case? Because if we have n colors and n vertices, what we can do is we can just assign a different color to every vertex, right? And now since an edge is between actually two vertices, So we can always be assured that the endpoints will have distinct colors. This part is trivial as every vertex can be colored or maybe will have different colors. So yeah, right. And yeah, will have a different color. And now note that we just don't need to show that it can be colored using n colors. Again, we need to find the minimum number of colors, right? So we also need to show that. Also, we need to show that. So, and we have provided an upper bound that we can always color using n colors. Now we need to show that we cannot do it using less than n colors. We cannot color the vertices using n minus 1 colors. And this is now what we'll be trying to show. Okay, so someone has joined the meeting. So hello SK. So I've just started a few. I've just started, and we are just on the like second question for now. So the first question was nothing, but it was asking like if we have a complete bipartite graph, then what will be the chromatic number of this graph? And we kind of showed that we can have a chromatic. This graph can have a chromatic number of 2. And now we are on the second question, and in the second question, uh, I'm just discussing like this. The problem is what is the minimum number of colors required to color a complete graph. So now we have a complete graph on n vertices, and now how many colors will be required? And I'm claiming that we'll always require n colors. So for showing that this n colors is the minimum number of colors required to color the complete graph, what we need to show is that we can color kn using n colors, and we also need to show that we cannot color it using less than n colors. That's when it will be a minimum, right? And note that coloring using n colors is trivial because we have n vertices, we have n colors, so every vertex can have a different color. And so every edge will have like distinct colored endpoints. So now we come to the second part, which is we need to show that we cannot color the vertices using just n minus 1 colors. That if we have n minus 1 colors, then we won't be able to color the vertices. And like, how do we show this? So to prove this, we can use something like contradiction to show that. So if, okay, sorry for this. So if there is any doubt, SK till now, or if you want to, if you have any doubts like moving forward, also you can just type in chat and I'll try to answer it. So yeah, feel free to ask any questions in chat. So now we need to show that Kn cannot be colored using n minus 1 colors. To show that Kn cannot be colored using n minus 1 colors, we will use contradiction, like we can use contradiction. And so when we use contradiction, so what we do is assume that Kn can be colored using n minus 1 colors. So let's just assume that Kn actually can be colored using n minus 1 colors. But now what happens is we have n vertices and we just have n minus 1 colors, right? Since we have n vertices, but just n minus 1 colors, then by pigeonhole principle, so you can think of like that we have n vertices and just n minus 1 colors. So this is similar to like having n pigeons, but only n minus 1 holes. So like at least 2 pigeons will occupy 1 pigeonhole. Like there will exist 2 pigeons which will be occupying the same pigeonhole. Something similar will happen here, that we have n vertices, but only n minus 1 colors. So at least 2 vertices will have the same color. So since we have n vertices, but just n minus 1 colors, at least 2 vertices. So maybe I should write by pigeonhole principle. PHP is pigeonhole principle. At least 2 vertices will have the same color. So let those vertices, so we just assume that let those vertices V1 and V2. So let's say there are two vertices V1 and V2, which have the same colors, like in the coloring of n minus 1 colors, right? But note that since Kn is a complete graph, so we have two vertices which have the same color, right? But now Kn is a complete graph. So in between every pair of vertices, we have an edge. If we have an edge between every pair of vertices, then we have an edge between V1 and V2 also. But in Kn, okay, there exists an edge between V1 and V2. And if there exists an edge between V1 and V2, but we have that V1 and V2 have the same color, then this is not a valid coloring, right? Because for every edge, the endpoint must have different colors. And hence, the endpoints of this edge have the same color, which is a contradiction. Like, why is this a contradiction? Because in a valid coloring, you cannot have, like, for all edges, each endpoint should have different colors in a valid coloring. But here we obtain an edge whose endpoints have the same color. So this is a contradiction. So Kn cannot be colored using n minus 1 colors, and we will require at least. Hence, maybe I should just write it down. Okay, not in bold. Hence, Kn cannot be colored using n minus 1 colors, at least n colors. So note that we require at least n colors, and we have also shown that we can do it using exactly n colors. So we have a lower bound as well as an upper bound. And that's why n is the minimum number of colors required. So yeah, I hope it's clear to you. Okay. Yeah. Okay, then I guess we can move on to the third question. So third question just asks, okay, SK is typing something in the chat. Okay, so SK is saying that I recall that it is proved that a map coloring problem needs maximum 4 colors irrespective of number of countries on the map. Obviously, that is not a complete graph, but how would we describe or characterize the graph representing such a map apart from saying that any point has max 4 countries making contact? Okay, so SK, I believe you're saying that you recall a result which says that we can color a map using just 4 colors. But here, like, we have that complete graph requires n colors, at least that's what I showed. So it might be a source of confusion. But note that this result of, like, I don't remember what is it. It is exactly like it is 4 colors or 5 colors. I'll have to check. But this result of coloring using maximum 4 colors. What I'm claiming is it is not for general graphs, but for planar graphs. Like, note that I hope you have gone through this week's lectures and you know about what are planar graphs. So planar graphs are graphs which can be embedded in a plane, right? So similarly, that you are saying that a map coloring problem needs 4 colors, right? So map is on a plane, right? Map is not in 3D space. A map is something which we draw on a plane. So a map corresponds to actually a planar graph. So in planar graphs, we need something like this, maximum 4 or 5 colors. But note that Kn is not a planar graph, right? Like, it has been discussed in the, I would say, lectures also, that like it has been discussed like in the third question itself it asks, right, which of the following graphs is planar. So it has been discussed in the lectures that K5, this graph, a complete graph on 5 vertices is not planar. So that's why it requires at least 5 colors. Like, like it is not an if and only if condition that if a graph can always, I don't know if it is an if and only if condition, but at least that's what like, that's what I know, that this result of like map coloring problem needing at max 4 or let's say 5 colors is for planar graphs. It is not for general graphs. So I don't know exact characterization, what would be the exact characterization of graphs which will require maximum 4 colors. But I know a very big subset, like planar graphs is a very big subset, right? So of graphs. So in planar graphs, we have that maximum 4 colors are required. I hope this answers your query. Good to know. Yes. So we can move on to the third question then. The third question is indeed about planar graphs, right? So which of the following graphs is planar? So the options are like K5, K33, K6, K4. So would you like to attempt it, SK? Would you like to answer this question, or should I just discuss it straight away? Like you can just guess any answer also if you want. Okay, so you're saying that D, that K4 is a planar graph. So yeah, actually, like this answer is correct. So good job. But I'll just for the audience who is watching on YouTube, I'll just go through the it option by option, like why is some option not planar or some option is not planar. So K5, like it has already been discussed in the lectures. I'll be assuming that you guys have gone through the lectures. So K5 is actually not planar, and this has been discussed in the lecture. Discussed in the lecture. And similarly, option B, the graph K3, 3 has also been discussed that it is not planar. So yeah, for these two options, we exactly know that these two are not planar. For option C, this graph K6 had not been discussed in the lectures. But note that K6 is a complete graph on 6 vertices, and K5 was a complete graph on 5 vertices, right? And we know that K5 itself is not planar. And K6 is just like a super graph over K6. So K5 is just a subset graph of K6. So if the subset itself is not planar, the superset can also not be planar, right? So that's why this is also not planar. Not planar because like as K5 is not planar. Yeah, K5 is not planar and K6 is just a superset of K5. So I hope you understand what do I mean by superset, that it's just like it just contains more vertices and edges over K5, right? And in option D, okay, maybe I should move the whole question to the next line. Yeah. So for option D, what do we have? We have the graph K4, and we need to, so while showing something is planar, we actually need to show its planar embedding, right? We need to show why is this graph actually planar. Like we could easily answer that these had been discussed in the lectures that they are not planar, and similarly we were able to answer this is also not planar. And but is K4 planar or not? Again, if it is not planar, we need to give some arguments. But if it is planar, we need to give its embedding in a plane, right? And actually, this turns out it is planar as it can be embedded in a plane. And what's the embedding? I'll show you the embedding also. as it can be embedded in a plane as shown in the given figure. And like, I'll show you guys the figure also. So yeah. So I just kept these figures at the end. So when we arrive at the actual question, uh, we discuss these. So you can see in this figure that this is the graph K4, like there are 4 vertices and there's a pair of, like between every pair of vertices, there's an edge. And like this can be embedded in a plane. And this is a planar embedding for this. No two edges are crossing. So that's why K4 is actually planar. And now maybe we can move on to the fourth question. So fourth question just asks how many edges are there in complement of P6? And like, what do we mean by complement of a graph? So complement of a graph means nothing but like we have the same vertex set, but the edge set is just the complement of the original set. Like if there was a set in the original graph, then there won't, if there was an edge between two vertices in the original graph, then there won't be an edge between those two vertices in the complement graph. And vice versa also. If there was not an edge between two vertices in the original, then there will be a edge between those two vertices in the complement graph. So this is what we have. So let's just see what should be the answer. So this is also not too hard of a question. So yeah. So total number of possible edges in a graph of n vertices is n choose 2, right? So if there is a graph on n vertices, the maximum number of possible edges is just n choose 2. But in a Pn graph, a graph of like a path graph of n vertices, I'm just deriving the bounds for like general n, not just for 6 vertices now. So a graph Pn just has n minus 1 edges, right? And why is this the case? Because this graph Pn is just a simple path on n vertices. A Pn denotes a graph which is just a simple path on n vertices. And like if there are a simple path of n vertices, then it has n minus 1 edges. So what do we get by this? We get that these n minus 1 edges won't be present in the complement graph of Pn. But the remaining edges which are not in Pn will be a part of complement graph, right? So total number of edges not present in Pn. So how many? Okay, sorry for this. So there are total possible number of n choose 2 edges, but Pn only has n minus 1 edges. So how many edges do we not have in this Pn? It is just difference of these two terms, right? I hope it's clear. If it is not, you can ask me in chat. So this will be total number of edges possible minus the n minus 1 edges which are present. Maybe I should just write it like total edges minus present edges, something like this. And this is equal to total possible edges. And this is just equal to this. So yeah. So this is the number of edges not present in Pn. So this is just the number of edges in the complement graph. So hence number of edges in complement graph of Pn is equal to this quantity. And if we put n equals to 6, like this is a general formula for a complement graph. Note that you don't need to remember this formula, like you can derive it easily. Like this is just a combinatorial bound, and this is also easy to see. And then like this n choose 2 minus n minus 1. Yeah, you don't need to remember this. So now we need to answer this for 6 vertices. So we just put n equals to 6. So, and if we put n equals to 6, so SK, would you like to answer what will be the answer if we put n equals to 6 here. So in this formula, if we just put n equals to 6, it will be just 6 choose 2 minus of 6 minus 1. 6 minus 1 is 5. So we just have 6 choose 2 minus 5. And this will just come out to be like a 6 into 5 by 2, which is like 15 minus 5, which will be just 10. Sorry for this. So this is putting just n equal to 6 in this formula, you can just obtain that. We'll get the answer as 10. So correct answer is 10. Okay. I hope it is clear to USK. If it is not, you can ask me in chat. Otherwise, I'll just move on to the next question. So now we have this fifth question where it's asked like, what is the chromatic number of the hypercube Q3? So let's just forget like, what does this hypercube Q3 mean? Let's just see this graph. So the question essentially asks, in this graph, in the graph given to us, what's the chromatic number of this graph? Again, SK, I would like you to try this out first. Like, I don't think it's too hard of a question, but it's easy to make silly mistakes in these kinds of questions. So I want to encourage you guys to attempt these questions. Otherwise, like these types of questions are the source of silly mistakes in the quizzes or the exams. So you can just try it out yourself. Like, what according to you should be the chromatic number here? So what is the minimum number of colors we require to color the vertices in this graph so that every edge has distinct colored endpoints? Okay, I guess. Okay, I guess there's some issue with SK's internet or something. He has disconnected. So I guess we can just. I'll just keep on discussing for the YouTube audience. So actually, the chromatic number for the graph shown in this figure will be nothing but 2. Like here, chromatic number will be nothing but 2, and we need to again like for showing that a chromatic number is 2, we need to show the coloring for which 2 colors required, and we need to show a lower bound of 2. So like it is trivial to get a lower bound of 2, as we have discussed earlier also, that every every 2 endpoints of the edge should have different colors. So we always need at least 2 colors. And now I'll show like what the how can we color this graph using 2 colors. So let the colors be C1 and C2. So let's say the colors are C1 and C2. Then we can just color the set of vertices. So we need to give the sets for the set of vertices for which we assign the color C1 and the vertices for which we assign the color C2, right? And now we can see that if we give a color of C1, then its neighbors B, E, and C should get a color of C2, right? Because endpoints should have different colors. So B, E, and C should have different colors. If these 3 have different colors, then let's say A had color C1 and the C, E, and B had color C2. Now let's suppose if B has color C2, then G and D should have different colors. And since we are dealing with just 2 colors, G and D should have color C1. And similarly, like neighbors of E should E also had color C2, so its neighbor should also have color C1. So A already had C1, G has C1, and F will also have C1. And similarly, like G and F both had C1 and D also had C1. So H will need to be C2 colored. And this will be a valid coloring, like we have considered all the edges and all edges have one endpoint as C1 and other as C2. So so we color the vertices A. So what do we color the vertices? Which vertices are colored C1? So A was colored C1, G and F were C1, and D was C1. So A, G, F, D with C1, and the remaining vertices like which are like just B, E, C, and H. B, E, C, and H with C2. So, like as I already considered, like you will just consider any edge, and it will come out that both the endpoints of that edge have different colors. So it can be easily seen that this is a valid coloring. Right. For any edge, consider just this edge EF. So EF is colored with C1 and E is colored with C2. And similarly, you can see for every edge. So yeah, that's why this graph has a chromatic number of 2. Let's just forget what does this hypercube Q3 mean. Like this is also a type of graph, but just the graph itself is this. So yeah. Okay, then I guess we can move on to the sixth question now. So sixth question says K22 is isomorphic to C4. True or false? So once again, I hope everyone knows what does isomorphic mean. So two graphs are isomorphic if actually the vertices of one graph can be relabeled so that the two graphs actually have the same edges in them. So like on a high level, like a graph G1 is isomorphic to a graph G2, like if G1 and G2 have the same structure. It's just that G1 has a different labeling of vertices and G2 has a different labeling of vertices. But like if there exists a labeling of G1 such that G2 and G1 actually become equivalent graphs, then that is what we call two isomorphic graphs. Like formal definition has been covered in the lectures, but on a high level, this is what isomorphic graphs mean. That the graphs which are essentially the same graphs, but they just have different labeling of vertices, and that's why we kind of think that they are different. So K22 is isomorphic to C4. So is this true or false? Like, do K22 and C4 graphs have the same structure? So, okay, so SK has joined again. So welcome back, SK. So I'm now just, I hope you have gone through, like, you have understood what does isomorphic mean. So the problem asks us this K22 graph, is it isomorphic to C4? Like, is this true or false? So actually, for this specific question, the answer is actually true. Uh, these two will be true. And why will these two be true? I'll just show you guys illustration for the same. Like for showing like a graph, for showing that this is isomorphic to this graph, we actually need to find a labeling for this graph, which is equivalent, which results in this graph C4. And I'll just show it to you guys. So, and this is true because let's just consider this figure. Right. Okay, so yeah. Consider this figure. So this is a K22 graph. First, let's just be convinced that this is a K22 graph. Why? Because the upper set of vertices are two vertices, and this lower set of vertices are two vertices, and every pair of such vertices has an edge between. So this is a K22 graph. And on a high level, what we can see is in this graph, actually, this graph is just a cyclic graph of four vertices. And why is this the case? If we start from this vertex, then if we go here, then here, then here, then here, back to the original vertex, then we have to traverse all the edges, and this is just a simple cycle. right? So on a high level, we can see that this is equivalent to a cyclic graph. And I just show the cyclic graph also. So yeah. So yeah. So if this was, let's say, if V1 and V4 corresponded to the upper set of vertices, if V1 and V4 were the upper set of vertices, and V2 and V3 were the lower set of these two vertices, were V2. If these two vertices are V2 and V3, these were V1 and V4, then we can see that actually these two graphs are equivalent. Like if V1 and V3 has an edge, then here also V1, V3 has an edge. If V1, V2 has an edge, then V1, V2 also has an edge, and so on. So this is true that these two graphs are isomorphic, as can be easily seen on the diagram of the two graphs. So these two vertices are, let's say, V1 and V4, and these two are V2 and V3. I should have put the labeling here also, but I kind of forgot. Then we can say that this is isomorphic to this graph. Okay, so SK has written something in chat. So uh, no worries, SK, like network problems occur from time to time. It's fine if you get disconnected due to network issues. So SK has a comment that visualized in 3D, we need a frame rotation to convert a K22 into a K4. Is that correct? SK, I don't think that K22, I think you mean not a K4, but rather a C4, right? Because uh, K4 will have a set an edge between all pairs of vertices, whereas in K22 you don't have a edge between like vertices on the lying on the same side. Like K22 is a bipartite graph, so like a bipartite graph, like K22 will not be equivalent to K4, like it is equivalent to like C4. And your query is like visualize in 3D, we need a frame rotation to convert a K22 into a K4. Is that correct? So visualize. Yeah, I guess you can visualize this in 3D. I don't exactly see like what do you mean by visualizing in 3D and frame rotation. But on a high level, like at least how I see like isomorphism is like just relabeling the vertices. Like if you can relabel to obtain the same graph, then that is what I call isomorphic. Yeah, but if you just want to say that like I get your point. You want to convert this graph to this graph. How will we kind of do this using rotations? So the high level idea is something like this. Like you can just take this vertex lying on the bottom left side and move it to upward somewhere on top. And now this crossing will move to the top side. And so we'll obtain somewhat of a quadrilateral. And that is exactly the C4 graph. Again, I don't exactly understand like what do you mean by frame rotation plus plane distortion? Uh, like, but I hope you still get a high level idea of like why I'm saying that we need relabeling of vertices, or you can just see here like I don't know like if we should rotate it in a frame like or plane distortion. But if we just put this vertex instead of putting this here, I put this somewhere here on the above side, then this will be then you can easily see that this will indeed be a cyclic graph. So it's just like embedding this vertex on a different side of the graph will result in it being planar. Will it result in it being similar to C4? Okay, cool. You get the idea. Thanks. Okay, then so I hope this seventh question is clear to everyone. Now the sixth question is clear, and now like we can move on to the seventh question. So seventh question asks us which of the following graphs is not Hamiltonian. So we are given a bunch of graphs A, B, C, and D option, like is none of the above. And now we need to answer which of the following are not Hamiltonian. So just once again revising the definition. So what is a Hamiltonian graph? So Hamiltonian graph. Bunch of spelling mistake. So yeah. So Hamiltonian graph is not nothing but a graph which contains a path of all n vertices. A graph which has a path containing all the n vertices. So note that by path we mean a simple path, and these kinds of definitions have already been covered in the lectures. Like no vertex or edge in this path, and yeah, but all the vertices should be present in the path, and this is what we call a Hamiltonian graph. And now to identify Hamiltonian graphs, actually like identifying whether a given graph or any given like the general problem of determining whether a given graph is Hamiltonian or not is actually a hard problem. Like it's a very hard problem. But there are some theorems which somewhat let us answer this question partially whether a graph is Hamiltonian or not. Like there are some theorems which are not complete characterizations of Hamiltonian graphs, but which give a partial characterization. And like one theorem is these theorems you have already seen in lectures, but I'll just revise them. So what Dirac's theorem, and Dirac's theorem says nothing but if every vertex has degree greater than equal to n by 2, then the graph is Hamiltonian. Sure. So this is what the uh, Dirac's theorem says. Like it does not give an if and only if, it only says that if every vertex has degree this, then graph is Hamiltonian. It does not say that if graph is Hamiltonian, then this should be necessary. Similarly, there is this Or's theorem, which says that if degree of u plus degree of v is greater than equal to n by 2 for every pair of distinct non-adjacent vertices u and v. So I hope you get what this theorem means. So this theorem just says that okay, yeah. So or like Dirac's theorem, I believe, was clear. And what does Bohr's theorem say? So for any pair of non-adjacent vertices, so any pair of vertices which don't have an edge between them, let's say those two vertices are u and v, if like degree of u plus degree of v is greater than equal to n by 2, and this holds for every pair of non-adjacent vertices. Like if every pair of non-adjacent vertices has, okay, this is not n by 2, but so if degree of v plus degree of u is greater than equal to n for every pair of non-adjacent vertices u and v, then G is Hamiltonian. Again, this is not a complete characterization. Like it does not say if G is Hamiltonian, then this condition should hold. It just again a partial characterization. Like if this condition holds that every pair of non-adjacent vertices have a sum of degrees greater than equal to n, then G is Hamiltonian. Okay, so I think SK is asking the chat, is there any significance to a tree or a graph with more than one component cannot be Hamiltonian? Yeah, so a graph which is actually disconnected. So SK, a graph which is generally disconnected, there can't be a Hamiltonian. It cannot be Hamiltonian always, right? Because uh, like you cannot go from one vertex of one component to another vertex of another component. So that's why generally when we talk about Hamiltonian graphs, we talk about only connected graphs. A connected graph. Like if we don't write connected graph, still I guess the definition goes through like all the graphs which have more than one component will always never be Hamiltonian, right? we can answer separately for each component whether one component will be Hamiltonian in itself, another component will be Hamiltonian in itself, but the graph as a whole will never be Hamiltonian if there are more than one components in the graph. So yeah, and there is nothing, I think, no significance to this. It's just like it's just a statement that a graph with more than one component can never be Hamiltonian. Sure. So I hope you see these two Dirac's and Wood's theorem. So just as an exercise, like what do you think is a stronger theorem? Like, can we say that Dirac's theorem implies Or's theorem, or whether like Or's theorem implies Dirac's theorem? Like, is one of these actually stronger? So SK is typing something in the chat. Okay, so SK is saying that Dirac's implies Or's. Are you sure, SK? I think it's the other way around. Like Or's theorem actually implies Dirac's theorem. Because let's suppose Dirac's theorem was true, that every vertex had degree n greater than equal to n by 2. But suppose there was a pair of vertices, one of which had degree 1 and another had degree n minus 1. Then according to Dirac's theorem, we'll say that it is not Hamiltonian, but according to Or's, we will say it is Hamiltonian. So Or's theorem covers a larger set of graphs than Dirac's theorem. And suppose Or's theorem, and like, why am I saying Or's implies Dirac's? Suppose Or's theorem holds. Like, suppose Or's theorem holds that if in a graph this property holds for every pair of vertices, then G is Hamiltonian. Then what I'm saying is Dirac's theorem will also hold. And why is this the case? Because if every vertex has degree greater than or equal to n by 2, then anyways we are sure that degree plus of u plus degree of v will be greater than or equal to n, right? Because this is greater than n by 2 and this is greater than or equal to n by 2. Okay, sorry for this, guys. What happened here? So yeah, I think I double clicked or something. So this part is greater than or equal to n by 2 and this part is greater than or equal to n by 2. And so sum will be greater than or equal to n. And hence we will get that G is Hamiltonian. Like if this condition of Or's theorem holds, then by Dirac's theorem also we can say that G is Hamiltonian. So that's why I'm claiming that Or's is a stronger theorem than Dirac's theorem. So just as a remark, Or's theorem is stronger than like Dirac's theorem. And what does this mean actually? This just means that that is Or's theorem implies Dirac's theorem. Or let's just say not stronger, but is a generalization of Dirac's theorem. So is this clear, SK? Why does Or's theorem imply Dirac's theorem and not vice versa? Like if Dirac's theorem, let's say for implication, what we have to say is like if you assume that Dirac's implies Or's, then we assume that Dirac's holds, then Or should hold directly. But it's not like direct because Like a degree u can be 1 and degree of v can be n minus 1. And still by Or's, we can say that graph is Hamiltonian. But by Dirac's, we won't be able to say that it is Hamiltonian. So that's why Or's is a generalization of Dirac's theorem. So this is just a remark, not relevant to the question anyways. But yeah. Now let's just go through these option by option. Like we have to answer which of the following graphs are not Hamiltonian. So let's just see. So option A is the graph Kn. So note that using these Or's and Dirac's theorems, we can identify the graphs which are Hamiltonian. But since these theorems are not two-way implications, so we can't say that, like, suppose if this property for a graph does not hold, then it is still possible that the graph is Hamiltonian. So it's not so this property can be used to partially answer if the graph is Hamiltonian, but this cannot be used to answer if graph is not Hamiltonian. Okay, 1 minute, guys. Yeah. So using these theorems, we can only identify which graphs are actually Hamiltonian, but we can't rule out that the graph is not Hamiltonian if these theorems are not satisfied. So for this graph Kn, actually, we can actually see that in the graph Kn, every vertex has degree of n minus 1, right? Since one vertex is connected to all other vertices. So like actually every vertex has degree greater than equal to n by 2. Because like n minus 1 is always greater than equal to n by 2. And so by Dirac's theorem, we can actually say that Kn is Hamiltonian. So maybe I can just write it down. So in Kn, every vertex has a degree of n minus 1, which is like n minus 1 is nothing but greater than equal to n by 2. So like by Dirac's theorem, Kn is like Hamiltonian. Right. I hope this is clear to everyone. Then we can move on to like option B. So option B is like the graph Cn, whether this graph Cn is Hamiltonian or not. So note that in the graph Cn, we cannot apply any of Dirac's or Or's theorem because in a graph Cn, like this is let's say this is the graph C4, it can be seen that every vertex has a degree of 2, right? Or maybe like not the C4 is a bad example, but in general, in a Cn graph also, every vertex will have a degree of 2. So, but if there are n vertices in the graph, then 2 is not greater than equal to n by 2, right? So we cannot apply Dirac's theorem. Similarly, if we look at Or's theorem, then we cannot even apply Or's theorem because for any two for like degree of u and degree of v will always be 2 and 2. Like in a cyclic graph, right? Every vertex has a degree of 2. So this will always be equal to 4, this sum. And this need not be greater than equal to n, right? If there are, let's say, 5 vertices, 6 vertices, then this sum won't be greater than equal to n. So by Dirac's or Or's theorem, we cannot say that Cn is Hamiltonian. So, but does this mean that Cn is not Hamiltonian? This is not true because Cn is actually Hamiltonian. And why is this? Because like Hamiltonian graph is a graph which has a path containing all the n minus 1 vertices. And now it can be easily seen that all the vertices can be traversed using just traversing the cycle, one side of the cycle, right? It is Hamiltonian. So like that's why I'm saying that even if these theorems fail, the graph can still be Hamiltonian. Like if this property fails, it does not mean the graph is not Hamiltonian. It can still be Hamiltonian. So it is Hamiltonian.
we can have a path containing all the n vertices by going around the cycle. Okay. So I hope it's clear. Yeah, so SK, we can just say it as a theorem that every Cn is Hamiltonian. Sure, like you can claim it as a theorem also, but uh, this is a very straightforward result. Generally theorems are results which have a bit more sophisticated proofs or something, right? We can just say that Cn is Hamiltonian. You are definitely correct. This is also a theorem, but no one specifically calls it a theorem because like this is like something very trivial to see. Whereas these things are not trivial and these had to be proved by these people till I can do. So that's why these are theorems. But yeah, nevertheless, like let's come to option C now. So option C is this graph K9, 9. So we need to answer whether the graph K9, 9 is like is it Hamiltonian or not? So again, we can just actually prove that Kn, n in general uh, is Hamiltonian. So what we can say is Kn, n is Hamiltonian. And why can we say that Kn, n is Hamiltonian? We'll need to show this, right? So we can actually show this using course here. And I hope I think you guys already have you'll already have the idea of how to use O's theorem here, but I'll just uh, type it out so that everything becomes apparent. So what do we have in O's theorem? That every pair of distinct non-adjacent vertices u and v should have a sum of degrees greater than equal to n, and then we can say that the graph is Hamiltonian, right? So in the graph Kn, n, we know that let's if one vertex lies on the left side and one vertex lies on the right side of the bipartite graph, then between those two vertices there will definitely be an edge in Kn, n. So the only vertices which don't have an edge between them, the only pair of vertices which don't have an edge between them are either the vertices if both the vertices lie on the left side or if both the vertices lie on the right side. So consider any non-adjacent pair of vertices u comma v. This can only happen if either both u comma v lie on the left side or both lie on the right side. So left and right side are the two partitions of the bipartite graph K and comma n, right? So suppose let's just say they lie on the left side. Like both these cases are similar. Suppose both lie on the left side. Then what we actually know is that what are the degrees of these u and v's actually? Like if a vertex lies on the left side, then it has edges to all the vertices on the right side, right? So there are n vertices on the right side, and any left side vertex will have edge to all of these n vertices. So degree of u will be n. Similarly, degree of v will be n. So actually, yeah, uh, it can be seen that degree of u is n is degree of u. And this is because if both lie on the left side, they will have all the edges to the right side vertices, right? So there are n right side vertices, so we'll have n edges for each of these degree, like u and v. So that's why degree of u is equal to n is equal to degree of v. So what we get is hence degree of u plus degree of v is greater than equal to 2n. So it may seem that, oh, we had to just show that it is sum of degrees is greater than equal to n, but we actually obtain it as greater than equal to 2n. So this is even stronger. But I just want to point out one specific thing here that uh, here n means, like in this theorem, n means a graph on n vertices. Like there are n vertices in the graph. Whereas here in this graph kn comma n, we have two n vertices, like n vertices on left side, n vertices on right side. So actually, like this theorem says the degree of u plus degree of v should be greater than equal to the number of vertices in the graph. So this n should not be confused with this n, because actually here the n denotes the number of vertices in the graph, whereas here the number of vertices in the graph is actually 2n, not just n. Although the final answer does not change, but this is something like I want you guys to keep in mind because it can be a source of silly mistake in some other question. So actually, degree of u plus degree of v is not greater than equal to 2 times the number of vertices. It is just greater than equal to number of vertices in the graph here also. It's just that the number of vertices here is 2n. So just don't confuse this n with this 2n. That's what I'm pointing out. So since number of vertices in kn comma n equals to 2n, hence by Ohm's theorem, we can say that k n comma n, okay, answer for this again, is Hamiltonian. So kn comma n is Hamiltonian, and like k9 comma 9 is just a special case of kn comma n, right? Putting n equal to 9. So this is also like Hamiltonian. So option C is also Hamiltonian, B is Hamiltonian, A is Hamiltonian. So the answer is option D, none of the above. Hence, option D is correct. Okay, so I hope this makes sense that why is kn comma n Hamiltonian, and especially this thing that number of vertices in the graph is not n but 2n actually. Right here, Ohm's theorem says that its sum of degrees should be greater than equal to the number of vertices. Like this n is just a variable, but it denotes the number of vertices in the graph. So this n has been replaced by 2n in this. So yeah. Let's move on then to the eighth question. Maybe I'll just put it on the next page. Okay. So eighth question says that let E be the number of edges. Let E be the number of edges, V be the number of nodes, and R be the number of regions of a planar graph. Then which of the following inequalities hold true? So which of these inequalities are uh, true for a planar graph? I think this has been like this should be somewhat trivial if you've seen the lectures. Would you like to guess, SK, which of these options should be correct? Yes, so SK is saying option B. So yes, actually you are correct, SK. So answer is option B is actually the correct answer. So option B is correct. And I don't think like much explanation is needed. You can just discuss like this has been discussed in the lecture also. But the high level idea, so high level idea for proving this sort of inequality. So I hope you know what are the regions and what do you mean by edges. Like edges are edges and vertices. We know what is an edge what and what is a vertex in a graph, right? In a planar graph, there is another concept of a region. And now to obtain this kind of inequality, what we can actually do is uh, we just sum up the perimeters of all the regions. So there are, let's say, R regions, and every region always has a perimeter and perimeter of a region is just the number of edges surrounding that region in a planar graph. So every region is always defined by at least 3 edges. So if we sum up the perimeters of the region, like all regions, sum of perimeters of all regions, it will be greater than equal to 3R, because there are R regions and each region has a perimeter of at least 3. So sum of perimeters of all regions will be greater than equal to 3R. But also note that it can also be seen that every edge actually observes in this sum of perimeters of all regions, every edge actually appears twice, because an edge can be adjacent to 2 regions at one time. And this is why sum of perimeters of all regions will actually be equal to 2 times the number of edges. So sum of perimeters of all regions is equal to 2 times the number of edges. And this sum is greater than equal to 3R, because R regions and every region has a perimeter of at least 3. So I just discussed the high level idea. I won't be writing this down because this has been shown in the lectures, but this is the high level idea. We just sum up the perimeters of all the regions. And from that, we obtain this inequality. So yeah. I hope now we can move on to the 9th question then. So 9th question says that a bipartite graph can have an odd cycle. Is this true or false? Okay, SK, any comments for this? This is also, I think, a straightforward question. Does a bipartite graph have an odd cycle? Like some of these questions, you can observe that they are quite simple, but I'm still explicitly discussing these in the as problem sheet, because in quizzes also there will be some easy questions, but there are chances of silly mistakes, right? So we need to avoid those silly mistakes, and that's why we need to explicitly discuss these kinds of questions also. Oh, okay, sure. You haven't seen this lecture yet. No worries, SK. I'll recommend though to we see these lectures before the quiz, because they can help you a lot. Okay, so but this is this question is asked: a bipartite graph can have an odd cycle. Is this true or false? So this is actually false. This is uh, I think we discussed this in last week's session also, that uh, a bipartite graph, in a bipartite graph, all cycles are of given length. And it's not too hard to see why is this the case, because in a cycle, you always start from one vertex and end at that vertex itself, right? And if we have a bipartite graph, suppose we start from the left side vertex, then if we have an odd number of edges, then we'll be going from left to right. If we use one edge, we'll be going from left to right. And then if we use 2 edges, we'll be coming back from right to left. And if we use 3 edges, we'll again be going from left to right. So if we have an odd number of edges and we start from the left side, we'll always end up in the right side. But in a cycle, we start from left side and we need to end at the left side itself, right? So we need to use even number of edges. I hope this high level idea is clear. This is just the high level idea of why a bipartite graph does not have an odd cycle, and it always only has even cycle, as all cycles are of even length in a bipartite graph. This has been discussed. Yeah. But the high level idea, at least, I hope is clear to you, that if we have a cycle, we start from left side, we need to end at left side, right? But if there are odd number of edges, we'll start from left and end at the right side. And that's why we can't have an odd cycle. Then I guess we can move on to the penultimate question for the day. So this is which of the following graphs is self-complementary? So what do we mean by a self-complementary graph? Again, so complementary graph was a graph, complementary graph is a graph's complementary graph is the graph which has all the edges not present in the original graph and none of the edges present in the original graph are absent from the graph. So complementary graph we know, and a self-complementary graph is nothing but a graph which is just a complement of itself. So yeah, so maybe I should just write it down. Self-complementary graph. And what do we mean by this? So a graph which is isomorphic to its complement. So note that instead of writing isomorphic, a very vague definition would be a graph which is like a graph which is complement of itself is a self-complementary graph. But note that like if you change the label of the complementary graph, if you change the label of the vertices of the complementary graph, then one might get confused whether a graph is a graph is self-complementary or not. And that's why to like unify the labelings and stuff, we say that it is actually isomorphic. So this is a more formal definition. Like a graph which is isomorphic to its complement is called a self-complementary graph. So again, let's just see option by option which of the following graphs will be complementary or not. So suppose we have the graph C6. So how? So first of all, like if two graphs are like isomorphic, then one condition is that at least they should have equal number of edges, right? If they don't have equal number of edges, then they cannot be isomorphic at all. If they have equal number of edges, still it is not sure whether they will be isomorphic or not. But if they don't have equal edges, then we are sure that they won't be isomorphic. So now here also like uh, we'll rule out some of the options whether they are isomorphic or not using number of edges argument. So you can see that C6 has 6 edges, right? Because it's a cycle on 6 vertices, so it has six edges. But it's complementary graph. So we discussed this in one of the previous questions also. So its complementary graph has like will have how many edges will its complementary graph have? It will have something like a 6 to 2, which are the total number of possible edges, minus the edges present in the original graph, which is 6. 6 to 2 minus 6, which is equal to, like we already calculated, it comes out to be 9. So, okay, I think, did we do some calculation wrong in the previous question? Oh, okay. I think that was a different question. So total number of edges possible are 6 to 2, and we have 6 edges already. So the number of edges in the complement will be 9 edges. So note that the original graph has 6 edges, its complement has 9 edges. So these cannot be self-complementary. Like, since these two edges cannot be isomorphic, right? A graph of 6 edges and a graph of 9 edges cannot be isomorphic to each other. So that's why it won't be self-complementary, since the number of edges are different in the complement. Hence, C6 is not self-complementary. So C6 is not self-complementary. Similarly, in option B, we get P4. And actually in P4, what we will get is it will come out to be self-complementary. It is self-complementary. And like I'll show an illustration for this also, like how does this come out to be self-complementary? Like just see this graph. Yeah. So if you can see this graph that this is the graph P4, right? A path on 4 vertices. Like consider the original graph as the graph containing just the blue edges. The graph with these blue edges is the original graph, which is the graph P4, right? This is just a graph containing a path on 4 vertices. So this is P4. And now note that its complement will be this red graph. So this will be the complement graph, right? Because these edges are absent in the original graph, but So this should be present in the complement graph. And note that this graph is again P4 itself. Like this red graph is also a path on 4 vertices. So both are P4. So we can always label the vertices for this graph such that it becomes equivalent to this graph. So that's why it is self-complementary. I hope it is clear to everyone. Why is it complementary? As can be seen from the below diagram. Where blue edges denote the original graph and red edges denote its complement. The complementary graph. It can be seen that both the graphs are P. Yeah, this is a P4 graph, this is a P4 graph. And now like they are isomorphic to each other. You can always relabel it. So yeah, two graphs are P4, then they can always be relabeled and hence are isomorphic. Okay, so I hope this is clear. If so, then maybe we can move on to option C. Option C is the graph P5. So actually in P5, we can show using similar arguments as done in option A that it won't be self-complementary. Maybe I just copy paste the argument for option A and I'll just change the values. So C5 we know has like, so we are given the graph P5, not C5, sorry. So we have the graph P5, it will have something like 4 edges, right? So its complementary graph will have, so total number of possible edges will be 5 choose 2 because there are 5 vertices and we already only have 4 edges. So number of edges present in the complementary graph will be 5 choose 2 minus 9, which will be, this will be 10 minus 4, which will be 6. So complementary graph will have 6 edges. So note that original graph had 4 edges, but complementary has 6 edges. So the number of edges are different in the complement. And so like the graph P5 is not self-complementary. So the argument almost remains the same as option A, but just the values have changed. I hope this is clear to everyone. If not, you can ask me in the chat escape. Otherwise, I'll just assume it's clear. And option D is like none of the above. So we already had option B. So none of the above does not apply. So hence option B is correct. Only option B is self-complementary. Right. Now we come to the last question for the day. So this question says that if we are given that G is a 3 regular, connected, simple, planar graph. So G has a lot of properties now. It's a 3 regular graph, it's connected, it's simple, and it's a planar graph. So these like what is a 3 regular graph? A 3 regular graph is a graph where like every vertex has a degree of 3. Right? And like connected graph is a graph where like all like the graph is a single connected component. And what's a simple graph? A simple graph is a graph where like no self loops are present and like between two vertices at most one edge is present. And planar graph is a graph which can be embedded in a plane. So why do we need these many properties? So, and we are also given that the graph has 18 vertices. And now we want to find out the number of regions in this graph. So we are given some properties of G and we are given the number of vertices in G. And we want to find out the number of regions. And how are we able to define the notion of region? Because the graph is plane. Since it is planar, we can define a notion of what's a region. Right? And generally, if we are given like something like if we are in planar graphs, if you want to find out number of something like edges or anything, number of regions, when we are given some other variables, the go-to formula is like a Euler's identity. And what does our Euler's identity say? That like for any, so Euler's identity only applies to these graphs. Like the graphs should be connected, it should be simple, and it should be plain. So if these three properties hold, like that's why G had these three properties, so that we could apply the Euler's identity. Like if G did not have any of these properties, then we could not have applied the Euler's identity. But since G has, we can apply. So for any connected simple planar graph, what we have is that R plus V is equals to E plus 2. What is R? R is the number of regions of that graph. V is the number of vertices. E is the number of edges of the graph. So for any this sort of graph, we have R plus V is equals to E plus 2. So from this, it seems that to find the value of R, we need to find the value of R, right? We need to have these two variables, V and E. If we have V and E, then we can use this formula to obtain the value of R. But we are only given the number of vertices in the graph, which are 18. So we are given that V is 18. But we are not given anything about this E. So we have two unknowns here, R as well as E. So we can't solve we can't solve one equation with two unknowns, right? So we need to figure out E in some other manner. So note that we have not used this property that G is 3 regular till now. And using this property, we will be able to find out number of edges in the graph. And why is this? So since G is 3 regular, this means that every vertex has a degree of 3 and there are 18 vertices. So what we can say is that sum of degrees of all vertices will be just equal to 18 times 3. And sum of degrees of all vertices is also equal to, in a graph, always equal to 2 times the number of edges. So from that, we can obtain the value of number of edges in the graph. Maybe I'll just. Since G is 3 regular, every vertex of G has a degree 3. So what we get is like sum of degrees of all vertices of G. So this is an equality which we know, like we know that like this is an equality not for this specific graph, but this holds true for all graphs. Like the equation that sum of degrees of all vertices is equal to 2 times number of edges. Like this is a very common property, and yeah. So if this equation is true, so maybe I should write it like this. We know that sum of degrees of all vertices is equal to 2 times the number of edges. So what can we say now? This implies that sum of degrees of all vertices is just like there are 18 vertices and each vertex has a degree of 3, right? So we just get 18 times 3 on this side, and this will be equal to 2 times number of edges, right? And from this, we get that like this is equal to 54. So number of edges is just 54 by 2, which is just 27. So number of edges is equal to 27. So we get this number of edges was this E variable, right? So we get this E variable's value as 27. We had this V as 18. So now we can find the value of R. So putting V equals 18, comma, E equals 27 in Euler's identity. What we get is that R plus 18 is equals to 27 plus 2. And from this, we get that R is just equal to like 27 plus 2 is 29 minus 18 is 11. So this is our final answer. So I hope it's clear to you. Okay, so SK had some doubts. Okay, so SK is asking that what is a simple graph? How is a non-simple graph defined? So SK, a simple graph is a graph in which there are no self edges. There is no edge there is no edge of the form which starts from the vertex V and ends at the vertex V. Like each edge should have two distinct endpoints. In a simple graph, like there can be self loops. In a non-simple graph, there can be self loops. Like an edge is between V comma V itself. And also another property in the simple graph is that there cannot be two edges between a pair of vertices. Like if there are two vertices, then at max one edge can be present. Otherwise, in a non-simple graph, we can have that between U and V, there are two edges present. So if these two properties are there, like no multi-edges between two vertices and no self loops, then that's what we call then that graph is called a simple graph. Okay, so SK had already written the answer also that we have 27 edges and R equals 11. So good job, SK. Your answer was correct. So yeah. Okay, this was, I think, the last question from my side for today. Yeah, so we covered stuff related to planar graphs and like isomorphism, graph isomorphism, and Hamiltonian paths, Dirac's theorem, Oates theorem, chromatic numbers. So we covered a bunch of concepts, questions covering a bunch of concepts today. I hope this session was helpful to you. And if there are any doubts, you can ask me in chat. We still have something like 10 minutes left. Otherwise, so SK is asking, are these questions from previous year assignments? So it's a mix and match. Some of the questions can be from previous year assignments, or some of them are like if I find some other questions also which I find very cool, then usually I add them also to this list of questions. So it's not necessary that every week the questions which I cover will be from previous year assignments. Like some of the questions, at least usually the hardest questions of the assignments are the ones which I don't take from the previous year assignments. But yeah. Okay, so will this be uploaded in the Swayam portal? So yes, SK, I believe you guys would have been given like a Google Drive link where I upload all these assignments. Do you guys not have that? If not, I can just post its URL in the chat also. So we upload these. Yes. So if you have, that's nice. So yeah, I'll be uploading this in form of PDF on that Google Drive link, and also I guess you also have the YouTube link for these videos also there. So I'll be posting this today's session's video also on YouTube. Okay, that's nice. So then if there are any doubts, then we can take them. Otherwise, if there are no doubts, then okay. So SK, I'll be uploading this video by I guess tonight. So yeah. I'll just usually as soon as the session gets over, I just upload the video. But uploading on YouTube also takes like 30 minutes or so. So it will be available by today. Okay. So I guess then there are no more questions for today. So once again, thanks for joining today, SK. So we covered a bunch of concepts, and hopefully I'll see you guys next week also. I'll see you next week also. Like next week, the timing will be like 6 to 8 p.m. on Monday. Today there was some issue with me while traveling, so we had to start the session at 7 p.m. instead. But usually we have the Monday sessions from 6 to 8 p.m. So hope to see you next week also. So it was good interacting with you, and yeah. Till next week, goodbye. I'll just you can leave the session and I'll just close the recording. So goodbye for now.